Imagine a microcontroller as the brain of an embedded system, ready to interact with buttons, lights, sensors, and displays. But how does this tiny brain know if it should be listening to an input or actively controlling an output, or perhaps even something more complex? This critical communication starts at its pins. Microcontrollers configure their general-purpose input-output, or GPIO, pins primarily through special function registers, often abbreviated as SFRs. These are memory-mapped registers within the microcontroller that allow software to control hardware features. By writing specific bit patterns to these SFRs, you directly tell the microcontroller how each GPIO pin should behave. The core mechanism involves setting individual bits within these registers to define each pin's role. For instance, a data direction register, or DDR, bit determines if a pin is an input or an output. Setting the bit to 1 typically makes it an output, while clearing it to 0 makes it an input. Beyond simple direction, other SFRs control features like internal pull-up or pull-down resistors, which prevent inputs from floating and picking up noise, or the output type, choosing between a push-pull configuration for strong driving or an open drain for wired logic applications. Some advanced microcontrollers also allow configuration of slew rate, which affects how fast an output signal changes, influencing power consumption and electromagnetic interference. To actually configure a GPIO pin, the process generally involves reading the microcontroller's datasheet to identify the relevant SFRs for the desired pin and function. Then, in your program, you write the appropriate binary value or hexadecimal constant to these registers to set the direction, enable pull-up or pull-down resistors, or select an alternative function for that specific pin. It is a precise, register-level interaction that gives you granular control over the hardware. A fascinating aspect of modern microcontrollers is pin multiplexing. This means a single physical GPIO pin can often perform multiple different functions, such as acting as a simple input or output, or serving as a transmit pin for a universal asynchronous receiver transmitter, or UART module, or perhaps an analog-to-digital converter input. These alternate functions are also selected by setting specific bits in dedicated multiplexer configuration registers, often called pin mapping registers, allowing flexible design choices without increasing pin count. Ultimately, understanding how to manipulate these special function registers for GPIO pins is fundamental to unlocking the full potential of any microcontroller. It allows you to precisely orchestrate how your embedded system interacts with the physical world, laying the groundwork for everything from simple blinky light projects to complex control systems with multiple sensors and actuators.